Good morning, Engineer Griffin. Good morning, Engineer Shirley. Can you hear me?
I can hear you.
Perfect. Good morning to our present. I am the director of the Human Resource Area, Sandro Arias Tello, of the Geotechnical Engineering Chapter of the Peruvian University of Applied Sciences. UPC. I would like to welcome you to today's second conference, the sixth day of our first International Geotechnical Congress. Yo voy a ser el encargado de hablar en español para el público presente y la ingeniera Shirley va a ser la encargada de hablar con el ingeniero Griffin. Este va a ser el orden del día de hoy y la estructuración que tendremos para hoy va a ser que primero vamos a presentar a GeoUPC, vamos a conocer un poco mejor al ponente Martin Griffin, que su nacionalidad es Inglaterra. Bueno, vamos a tocar el tema de Global Industry Standard on Tiling Management, o en sus iniciales Gistm. Y como ustedes saben, los que han estado asistiendo a nuestras conferencias durante toda la semana, al final de toda la ponencia va a haber una ronda de preguntas del público en general que se encuentre presente, que pueden ir formulándola desde ya para poder preguntárselas al ingeniero Griffin. Ok, como ya varios saben quiénes somos, el equipo GeoUPC, somos un equipo conformado por alumnos de la carrera de Ingeniería Civil de la UPC y tenemos como razón de ser nuestra formación como profesionales en el ámbito de la geotecnia. Nosotros conformamos un espacio crítico y de investigación donde participamos y creamos actividades para la comunidad estudiantil con el objetivo de promover y fomentar nuestro desarrollo personal y profesional. ¿Pero por qué hacemos esto? Para poder llevar todo lo aprendido de manera teórica a la práctica. Ok, el tópico que vamos a tocar el día de hoy va a ser geotecnia aplicada a la minería. El tema Global Industry Standard on Tiling Management. El ingeniero Mr. Griffin, esta es su hoja de vida, su bibliografía. Es ingeniero geotécnico con especialización en proyectos mineros. Cuenta con más de 25 años de experiencia en ingeniería geotécnica. Actualmente labora para la consultora internacional Nike Personal en Londres, Reino Unido. Realiza labores de ingeniería geotécnica para proyectos mineros internacionales y a nivel conceptual hasta el cierre, incluyendo presas de relaves, pads de lixiviación e investigación geotécnica. Ha participado en varios megaproyectos de ingeniería civil en el Reino Unido. Actualmente es miembro del Consejo de la Sociedad Geológica de Gran Bretaña y miembro de los comités en otras asociaciones nacionales, asociaciones de especialistas en geotecnia y geoambientales. Es revisor se encarga de revisar revistas internacionales para GEOGH y IAEG y es mentor de grupos sobrepresentados. Bueno, sin más que decir, el ingeniero Martin Griffin tiene una excelente hoja de vida, pero bueno, por mi parte ha sido todo. Voy a darle el pase a la ingeniera Shirley que nos va a explicar los mismos procedimientos, pero ahora en inglés para el ingeniero. Shirley.
Welcome, Engineer Griffin, to the first International Congress of Geotechnical Engineering at Peruvian University of Applied Science. We have met before, but now we're in this day. We feel very pleased to come with your presence today, and we'd like to thank you in advance for letting us to learn from you on the topic that you're managing today, Global Industry Standard on Tiling Management. So I'm going to talk about your experience first. You are a geotechnical engineer with a specialization in mining projects. You have more than 25 years of experience of geotechnical engineering, currently working for the international consulting firm Princeton in London, United Kingdom. Have been performed before geotechnical engineering work for international mining projects from concept to closure, including tailings dams, leach pads, and geotechnical investigation. Has participated in several civil engineering mega projects in the United Kingdom. Currently a member of the Council of the Geotechnical Society of Great Britain, as a member of the diversity committees of the National Association of Specialists in Geotechnics and Geoenvironment, and also the International Journal Reviewer for CIIGGUPC, and also the EAEG, and a mentor for underrepresented groups. You have very extended experience, and we want to learn from that. So if you don't mind, I'm going to pass you with the Professor Roman, who is about to say some welcome words to you, who is also a pleasure to have you here. Por favor, Professor Roman.
Thank you.
If you like to say hello to the engineer.
Well, hello, Martin. My name is Brian. We were in touch through LinkedIn for the Peruvian University of Applied Science. I would like to thank you for your willingness and kindness to be part of this event and to share your knowledge with the South American geotechnical community. To give some background, the mining industry plays a very important role in Peru's gross domestic product. Moreover, we're the second largest producer of copper in the world. There are many large companies that have projects in our country, such as Anglo American, Freeport-McMoRan, BHP, Glencore, Rio Tinto, and we're currently struggling to implement the Gistm in our tailings storage facilities. So I'm pretty sure that this lecture is going to be very useful for all of us who are in the mining industry. I think we will learn a lot from your experience. So thank you again, and please start.
Okay,
with
I
your
will just
lecture.
I will just start share my screen. You see my screen, everyone?
Yes, engineer, we can see you
Okay.
very well.
Okay.
Thank you.
Thank you very much for the very kind introduction. And I'm going to talk today about the global industry standard on tailings management and a bit about tailings management in general, because it's generally misunderstood what it really is and what it really isn't. And this is a very brief introduction just to give you a flavour about it all. Okay. I'm going to talk a bit about myself, a bit of informal introduction, so you know I'm not just an engineer. I'm going to be looking back at why mine waste facilities fail, a bit about the global industry standard on tailings management. Then I'm going to look at why on projects mine waste facilities, and then a bit of words of wisdom that I've picked up on about 25 years experience that I would like to pass on to you younger ones. But you can use on any project, any sort of geotechnical project. I thought it might be useful just to pass a bit of wisdom on, or a bit of my grey hair to you. Okay, a bit about me. I was born in 1971 in Northern Ireland. I grew up in Cornwall, which is a historical mining area in England. They had copper and tin mines, and they're mostly underground mines. I moved around England. I graduated in 1995 with a 2-1 degree from Clermont School of Mine. I'm married with one wife. I live in Kent in Ashford, which is near London. I'm called something in the United Kingdom called a ground engineering professional. I'm a chartered engineer and I'm a chartered geologist. I love football. My football theme is Liverpool. I love Liverpool and I love science fiction, especially Star Wars. I'm a geologist. I'm an engineer. And an engineer and a geologist see things very differently sometimes. Like an engineer sees things in numbers, an engineer sees things in pictures. And very difficult mindsets. We see things very differently. Like a geologist thinks a lot, an engineer likes to tinker around with problems. Geologists like uncertainty, things that they don't know. Engineers like order. So this helps me when I'm doing tailings management. I have to see both sides of the picture. As an engineer, as a geological engineer, I've done all other things in my career. I've done rock mass classification, planning ground investigations, ground models, remedial works, foundation design, piling, foundations, risk registers, sequence analysis, site supervision, writing reports, and a bit like Boba Fett. We call it in the United Kingdom a jack of all trades. I graduated in 1995 as a graduate, did some research, did some into clay deformation and pastes and how they behave, did logging, worked in labs. Then I specialised in mining geotechnics, working on open pits, tailings, dams, wastewater dumps and haul roads. And I'm now specialising in risk and mining geohazards with Knight Piésold again. I joined Knight Piésold in 2001 originally, left them, and now coming back to them. But I've specialised in mining geotechnics for about 20 years and mining tailings dams for about 20 years. But as I say, now I'm really focusing on the risk aspect. But this talk's going to talk about generally tailings dams in general, global industry standard on tailings dams. So looking back and why mine waste facilities fail. We've heard of all these stories in the press. Mount Polly in 2014, Bruandino in 2019, and Fontaine in South Africa only this year. And these are tragic cases, and we don't want anything really like this to happen ever again. So what are tailings? Tailings are the materials left over from the process of separating the valuable fraction from the uneconomical fraction, that is the mine waste from an ore. They generally include fine-grained particles, chemicals, minerals, and water. Depending on the type of mining, minings can be a liquid, a solid, or a bit of both. Tailings characteristics can vary from project to project and deposit to deposit. It depends on the ore mineralogy, the host rock geology. It could be an oxide, a sulfide, a carbonate, or native minerals like gold or occasionally silver. The tailings characteristics can depend on the ARD, the geochemistry, how high the pH is or how low the pH is, if it's oxidized, if it's reduced or reduction. And they also depend on the physical and chemical processes used to extract the valuable minerals. If it's got cyanide in, that affects the tailings characteristics. As time progresses from 1840 in the bottom left-hand corner here to 2005, and as we go to now 2030, you can see that the ore grade has decreased with respect to time. But as the ore goes down, ore grade goes down, the amount of tailings goes up, and therefore the tailings dam or the capacity you need to store these tailings and mine waste has to increase to cater for the increased amount of tailings being produced. So, as I said, we've seen all these cases in the press. When you've seen one tailings dam failure, you've only seen one. And it takes more than one specialist to see why they went wrong. But there's no one solution to fit it all. We have to look at them individual, case by case. And when we design them, we do exactly the same. We have to look at them individually. We can't just say, we've worked on one project and then working on another project and copy bit. We can use ideas, but we can't copy everything word for word. So when you hear about a tailings, where do you hear your news from the tailings? Do you hear them from your friends? Do you go to Google where everyone's talking about it and saying how bad tailings are and how bad mine waste facilities are? Or do you go to some unreliable sources on the internet saying, again, mine waste is bad? Or do you go to trusted sources? And there's a really good website I'd recommend to anyone who's interested in finding out more about tailings news. There's something called Tailings News Alerts. They print about a monthly newsletter about all the news about tailings in the world. So what makes tailings management facilities unique? Well, if you compare them to water retention dams or something like a reservoir, they're very different. Water retention dams, or WRD, the owner has a substantial amount of resources. That is, they have a lot of money available. They're viewed as useful, they're valuable, they store water. They're constructed in a single stage, and they have a finite operating life, year zero to the end. But when we compare them to tailings dams, they're very different. Tailings dams aren't seen as a cost, they're just seen as mine waste, and they're imposed by the mining economics. Construction is ongoing. As you produce more and more ore, you produce more tailings. The cost spreads out during the cost of the project. The owner isn't really focused on dams, they're focused on mining, and they're focused on profits generally. And tailings is the last thing they really think about. And they should be designed to last forever. So it's year zero to forever. So in the past, there were very, very, very bad ways of depositing tailings. And these are some pictures. So you can see all the mine waste going into the river. And then you get a failure like that, as we've discussed briefly. So there are new ways, new drivers for modern tailings management. This depends on the economics of the mining venture, the protection of the environment, And these two drivers impact tailings management and the manner in which the tailings management facility is designed, constructed, operated, managed and closed. We do a lot about sustainable development now, stewardship of the land and the water. The type of tailings to be managed, note, I don't not say stored, management is more covers the water facility, the water engineering, as well as the tailings slurry or the tailings composition, not just the water piping and all that. And we have to understand understand a range of realistic alternatives of tailings management systems available and how they can be effectively utilised throughout the project benefits. So there are many things that can go wrong on the tailings dam. They can be constructed with minimal control. They can be constructed with poor bedrock or poor foundations. Can be constructed too fast with an upstream. We're going to come back to this later. They can be constructed too steep on a downstride slope, and I'll talk about a bit about this later. And they have a potential for failure in static liquefaction or in seismic activity or flooding. But there's so many things that could go wrong. So you have to cater, when you design them, you have to cover all these eventualities. And sometimes your brain can just go absolutely crazy because you think you've missed something. But I fortunately work in a very good team, and we talk and we share ideas and we have everything checked. Oh, okay. All bad examples. We've seen Meresbrook in South Africa, 17 fatalities, and 600 people injured. This is incident in Hungary, another bad example. So how can we reduce these problems? As I say, efficient design, efficient operating and management, efficient closure, competent design, competent management. We have to control the water, and these are the dominant factors to how we can reduce these problems. But now we can learn from good examples as well. For example, this project in Spain. Or projects in Eritrea, for example. Yeah, the frequency of failure, this is quite an old report, but the statistics haven't really changed. But a lot of that, probably there's about a failure rate of about 1% per annum when you consider about 18,000 tailing sites. These are all the main causes of tailing dam failure, ranging foundations, slope instability, unusual rain, static seismic liquefaction, management operation, but a lot of them are generally water controlled. So if we get a handle on the water, we have a good handle to minimize the failure. Tailings management in the past traditionally has been seen as like an elephant in the room, and every expert has an opinion, but we have to see the big picture and how everything's linked together. Somebody say the environment says a fan or a spear, or as me as a geotechnist, I say it's a snake, but we have to see it all together as an elephant. So what these interim conclusions, these immediate conclusions, we have to understand the tailings dam design. We have to understand the regulations, and this is when we come into talking about this new standard, the GISTM. Education comes from good examples and common sense, coming back to basic engineering principles. So now I'm going to look big and look at the global industry standard on tailings management. Okay, the global industry standard was really introduced about 2020, and I'm going to talk a bit about it now. Okay, before 2020, there was a lot of high-profile reports, and as tailings failings happened, more and more reports got published and talking about the causes of the report, ranging from the Mount Piley reports, Fernandinho, Caddo Valley operations, and these all highlight why the tailings dam failed. Other reports were published about 2019. And it talks about like the expert panel on the technical causes of the failure. As I say, Mount Polly, Cadna Valley, all talked about foundation failure, Fernandinho, static liquefaction. And then they use modern testing and analytical processes used to sort of model them and back analyze what happened. But then they wanted to look at the immediate causes. While there are no technical reasons why tailings dams fail, overall the technical governance systems of the tailings management is the most important cause. That means the people who operate us, not just the design issues. So it's important upon the managers of the tailings facilities to develop a better understanding of the system to successfully operate for safety. So after Bruandinho, they found out that the company Vale, their operations were siloed. That means people working in isolation. We said about the elephant, everyone was looking things into isolation. And the company lacked transparency. And there was also echoing of independent reviews of the company structure, found that bonuses of employees in the GeoTechnia area overseeing the geotech safety were linked to almost exclusively to financial targets, with safety goals representing a small proportion of the compensation metrics. That means they were more incentivized by money rather than looking after the safety of the facility. And this was outlined in the report here. Also, Mount Polly's, another report that was issued talking about the failure of Mount Polly, and they did a root cause analysis which drills down to get to the bottom of the cause of the failure. And they call it a root cause analysis, which is used to identify the specifics and interaction of various factors which played a most important role in the failure. The outcome of the root cause analysis, event and causal factual tree is shown in the report. This is on the second illustration with the blue, the yellow, and the red and green sort of circles, and it just tries to highlight what was the root cause and the main important cause. Okay, but when you start a mining project or when you start a tailings dam, you have to ask yourself where you are in the mining project. Are you starting at the concept? Are you mining? Are you in closure? And this depends. We have a lot of uncertainty in the green and on the orange, and this is where we usually operate, or myself as a consultant, I usually do. Myself as a consultant, I help design, manage tailings dams. So I help to eliminate, select, refine, design, and construct. But we have different, as the project progresses, we start from about 30% to a 50% accuracy, ranging down to 10 to 15% accuracy. And then this slot has various options, from a full range of options of tailings management facilities down to one or two options for the client to select which they feel is the best. Secondly, ask yourself what is really important to a mining project. And this comes out to anyone who's working on a mining project. There has been these case histories in the past that led to the global industry standards had sort of said there are things that are constraining the complex system. These are economic boundaries, safety boundaries, and workload boundaries. And if you work out within these, decision making within these constraints may contribute to failure. So if you're pushed for costing, your quality may be jeopardized. If your time may be compromised, your quality may be jeopardized. So you can't, if you try to get something too cheap, you may get something bad quality. So it's getting that balance right. Myself as a consulting engineer, I find it very demanding, frustrating, but rewarding with these constraints demanding because it occupies most of my time and concentration. It's frustrating because I would usually work with incomplete data or very small sample size, or someone's just sampled one bit of tailings, say that's represented the whole of the tailings area. It can be rewarding because I'm using my passion and my talents to the full. And I keep having to remind myself not to panic. So tailings dams are considered complex systems. And this was first coined by an author in America who was a pioneer originally, called Sidney Dekker. And these characterize why a tailings dam may fail. And this was the link, what they came up with the Global Industry Standard on Tailings Management. Or what's the most important bit? They talked about the importance of the small, unrelated items, obeying and applying guidelines and standards. Models are a simplification and may be wrong. Working under international and national regulations and standards and guidelines. And importance of diversity to build resilience. And I'm going to talk about these next. Importance of the small, unrelated items. A series of small, apparently unrelated decisions may long-term significantly impact the outcomes of a system impacts, and they are usually misunderstood and neglected. For example, in the United Kingdom, we have a lot of plastic straws or plastic sort of rubbish in rivers and seas, and they build up and they pollute the environment and destroying ecosystems. So it's these small things that affect the big things, but they may be all seen as interrelated, unrelated items. Secondly, it's the sum of the interrelated parts that make a complex system. A system of conditions that are interrelated that can have significant impacts on outputs or outcomes due to the series of decisions that are misunderstood and neglected, and neglect the interdependencies. And you can see by this drawing, there's so many circles that link to other circles. And in a tailings dam, as I said before, there's so many things that are interlocked that you have to think about the big picture, not just things in isolation. Models of simplification may be wrong. There can be unknowns, and there can be effects that are not effectively evaluated due to incomplete information or other factors. Models can't capture everything, but models are just a simplification of reality. For example, we could do a slope stability. We can do it factors resisting equals factors resisting divided by the sliding forces to get the factor of safety. Just a very, very simple calculation. So tan theta over tan beta. So the slope of the tan of the angle of resistance over tan of the slope angle. Or we could do a very simple spreadsheet to do a factor of safety. But we may not have enough, we may have a very simple observation there. We could do a limit equilibrium thing of a tailings dam, or we could do finite element. But then we still have to remember models of simplification I may be wrong. As someone once said, all models are wrong, but some are useful than others. But like, for example, I would do this, the very, very simple calculation, tan phi over tan beta, just to get an approximation, but it would not be as good as a Praxis model, but it depends on the quality of data, cost, and how much data I have. As a consultant, we have to, and mining projects and tailings dam, we have to obey international and national regulations. These are measures and procedures that must be identified and applied in the day-to-day approach to the management of complex systems, like a tailings dam. The importance of diversity to build up resilience. As with diversity, the larger number of perspectives to view a problem, as I said before, comes up with better solutions, and probably we're more likely to get derive a correct answer the more people we ask, and to get consultation involved. As a tailings dam fails, it's something called a normalization of deviance. This is any significant departure from what is considered the normal. So if we're going in true north and walking instead by magnetic north, we are going to deviate several degrees off our target. So therefore, I'm saying the behaviour that departs from north, i.e. departing from what is standard, is typical from a given situation. Normalisation of deviance suggests that the unexpected becomes the expected and becomes what is expected. We must learn from other sectors and other industries, such as aviation, NASA with the space shuttle accident, healthcare and shipping accidents. We can't just limitize our safety management approaches based on tailings management. When we're looking at a tailings management system approach, we look at these circles here. So we consider the planning, the design, the construction, the operation. And these are all related to the community, the regulators, the independent reviews, and senior management. And that's all makes up the mining system. So we have data management issues, we have planning, but data management related to planning and design and operation and construction. And those related to the community, regulations, local regulation, related to senior management and independent review. So what does a simple system look like in its simple sense? We have it's an interrelation between operating environment, other interfaces, hardware systems, and then we get things like process and procedures coming into play, support equipment and software. This is for another system, but this shows how it's all interrelated. Mine tailing systems are complex systems and have so many dependencies, things related to one another, competitors, relationships, and interrelationships. And it can be dependent on the performance, interconnections, environmental impacts, the variability, the safety, the price. There's so many things that contribute to a complex system. Let's say an inherent tailings dam may not just fail because of one reason. There may be a lot of reasons. This is called a Swiss cheese model, based on Swiss cheese, which has traditionally got holes in it. So you have all these layers of failure, like organisation influences in the dark blue, operation errors in the medium blue, then the design failures, and then unsafe acts. And as these are the inherent weaknesses, they're weaknesses within the system, not flaws, they're just weaknesses, and then it will be exploited and eventually lead to an accident. So back to what we were talking about, the global industry standard on tailings management. This was compiled during the Global Tailings Review Report project. It's in various languages ranging from English, Spanish, Portuguese, French, and Chinese. So there's no excuses not to read it. There are 3 conveners: the International Council on Mining Metals, the United Nations Environmental Programme, and the Principles for Responsible Investment. It first came out in 2020, that's version 1, and there's going to be another revision this year or next year. The ICMM, which is the International Council on Mining and Metals, have specific targets to reach. So what does the GISTM contain? Well, there's it contains 6 topics talking about the affected communities, an integrated knowledge base, design, construction and operation and monitoring of the tailings facility, the management and the governance of the tailings facility, the emergency and response and long-term recovery if something bad happens, or catastrophic happens, should we say, public disclosure and access to information. And within the GISTM, it contains 15 principles and 17 requirements. It's over to you to read it and apply and design and teach others. So, topic 1 talks about affected communities. Respect the rights of project affected people and meaningfully engage them at all phases of the tailings facilities life cycles. So it's from when the project becomes a concept to closure. Topic 2 is an integrated knowledge base. Develop and maintain an interdisciplinary so that everything related together knowledge base to support the safe tailings management throughout the tailings facilities life cycle, including closure. 3, using all elements of knowledge knowledge base, the social, the environmental, the local economic, technical to inform your decisions throughout the tailings facilities life cycle, including closure again. Topic 3, design, construction, operation, monitoring of the tailings facility. Principle 4, develop plans and design criteria for the tailings facility to minimize risk for all phases of its life cycle, including closure and post-closure. Principle 5, develop a robust design that integrates the knowledge base and minimizes risk of failure to people and the environment for all phases of the tailings facility's life cycle, including closure and post-closure. Topic 3, design, construction and operation monitoring of tailings facilities. Principle 6, plan, build and operate the tailings facility to manage risk at all phases of the facility. Principle 7, design, implement and operate monitoring systems to manage risk at all phases of the facility life cycle, including closure. Topic 4, this talks about the management and governance. Establish policies, systems and accountabilities to support safety and integrity of the tailings facility. Principle 9, appoint an engineer on record. So that's employing a consultant to help the mine operate in a safe and effective way. Topic 4 continued. Principle 10, establish and implement levels of review as part of a strong quality and risk management system for all phases of the tailings facility's life cycle, including closure again. You can see closure is so important, not just the operating of the mine. Principle 11, develop an organizational culture that promotes learning and communication and early problem recognition. Principle 12, establish a process for reporting and addressing concerns and implement whistleblowing protections. So if someone spots a leak in one of the or a burst pipe on the tailings dam, there is a safe mechanism for someone to report a problem without having any repercussions from management. Topic 5, emergency response and long-term recovery. Principle 13, prepare emergency response to tailings failures. Principle 14, prepare for long-term recovery in the event of catastrophic failure. Topic 6, public disclosure and access to information. Public disclosure and provide access to information about the tailings facility to support the public accountability. So that's basically being transparent with the public, because mining has got such a bad reputation with the public, and it's up to us to share the information with the public. So in the global industry standard on tailings management, there's lots of definitions, and it's, for example, a catastrophic failure. A tailings failure can result in material destruction to the social, environmental and local and economic system. And these failures can be a function of the interaction between the hazard exposure, vulnerability, and I'll talk about this a bit later, and the capacity of the people or the systems to respond. Catastrophic events involve numerous adverse effects at various scales and timescales, including loss of life, infrastructure, and catastrophic failures exceed the capacity of the affected people to cope using their own resources, triggering the need for outside assistance in emergency response and restoration and recovery efforts. A note on disaster risk. There's a disaster risk which is hazard multiplied by vulnerability, and this represents a function of the hazard exposure and a person's vulnerability. And this sort of Venn diagram shows the relationship between hazard, exposure, and vulnerability giving a risk. So the risk is the likelihood of the loss of life, injury, and destruction and damage from a hazard in a given period of time, and it's related to the hazard, the vulnerability, and the exposure. So it's not just a simple probability of an event happening multiplied by the impact of the consequence. When we look at risk, we look at risk on various aspects. So risk isn't generally always seen as a risk, the probability multiplied by the consequence. We can see risk impacting the cost in the pale blue, the environmental impact, the sort of legal aspects, the public, the sort of public safety, and how much it's going to cost the mining operator. Hazard has usually multiple causes, and it's not just one aspect. It's cause 1, 2, 3, 4, and then we can have multiple accidents because of these various causes based on just one hazard. But we need, on the far right, we need effective mitigation to prevent these individual causes happening. So we need something called a safety management system, and it's not just simple risk management. This talks about the safety governance, which oversees the mining operation and the tailings operation, the safety organisation, make sure that's in place, a system safety programme, and a safety culture. When we look at tailings dam, we have to look at the most credible failure modes and scenarios. Given the materials present in the structure, its foundation, their properties, their configuration, how the tailings dam has been constructed, the drainage conditions, the surface water, and throughout its project life. We look at the credible failure modes can and do typically vary during the lifetime of the tailings facility. A facility that is appropriately designed and operated considers all these credible failure modes and includes sufficient resilience against each of them. Different failure modes will result in different scenarios. Credible failure modes do not exist for all tailings facilities. And I say here, finally, it is not associated with the probability of the event occurring, and having a credible failure mode is not a reflection of facility safety. So what sort of things can happen? As I said before, a tailings dam has about 4 key main failure modes: overtopping, mass movement, internal erosion, or surface erosion. And from those 4 main failure modes, you can get adverse conditions. And there's various signs you can look at when you're doing a site inspection or when operators are doing their work. As a consultant, we have to help clients do design basis reports. This provides the basis for the design, the operation, the construction and monitoring, and the risk management of the tailings facility. We talked a lot about the knowledge base on the introduction to the GISTM. This is the sum of the knowledge that's required to support the safe management of the tailings facility throughout its lifetime, from concept to closure. The knowledge base has an iterative nature. That means it changes. It doesn't just keep static. It needs to be updated when the need arises and the context changes. It's based on detailed site characterization, baseline knowledge of the social and environmental context, as well as the design, construction, performance monitoring. And it should end with data collected as the project evolves and knowledge evolves. The Global Tabling Industry Standard on Tailings Management also mentions a lot about the observation method devised by PAEC in 1969. I'll just bring out this what the observation method is. It's the proactive assessment of the design stage of every possible unfavourable situation that might be disclosed or identified by the monitoring programme, and the development of an action plan to mitigate an action to reduce the risk in case the unfavourable action or situation is observed. So you're trying to reduce that risk or that hazard before it actually happens. Other definitions: preliminary design. For the purposes of the standard, preliminary design is a design performed at a level sufficient to determine the differences between the viable designs that adopt different external loading design in terms of required footprints, volumes, drainage requirements. And we aim for safe closure. A safe closure talks about a closed tailings facility that does not pose ongoing material risk to people and the environment, which has been confined by an independent tailings review board member, and it has to be signed off by an executive. So looking a bit about tailings facilities generally, what are the drivers? Scarce water, environmental, social, government implications, land availability problems, economics, confidence in dewatering system, regional trends in Canada, Australia, EU and Brazil are driving tailings management. And there's more and more responsible mining operators now, and they want to invest in best practice. And improved industry recognition that tailings can be managed effectively with the benefit of the project and their reputation. Questions to ask yourself at the start of the design: what's the tonnage? What are the environmental constraints? How much water is available? What is the climate? What is the topography? Is the area subject to earthquakes? Do the tailings have any potential for acid mine drainage? What is the geotechnical characteristics and properties of them? Are there permitters requirements? What is the construction material? Where is it sourced and where is it from? What with the closure? Can you just dump it? I don't think so. But let's look at water. Water controls tailings and how you deposit tailings. You could deposit as a slurry and build a tailings dam, or you can do thickened tailings of paste as a sort of dam, or you can decide in a filtered tailings, which is a dry cake. They both have very different properties and very different sort of way you deposit and have different sort of impacts, like different seepage issues and different costs. But as you see, slurry has less water, has more water than a filter cake, Terry. So tailings slurries talk about 25 to 30% solids, 25% 30% pulp density, and then when you have a pulp density in a filtered cake, you have about 65 to 70% solids. You could build a tailings dam for slurry from an upstream. This is an upstream tailings dam. This is highest risk, suited for low seismic areas. It's not recommended for water area where you've got water bearing materials and high saturated materials. Based on rate of rise about 3 to 5 meters per annum. They're not suitable for areas, I say, with static liquefaction. But these are very high risk, and some areas, like in Brazil, they're not legal to build. Downstream is another form of construction for slurry deposition. These are low risk, high cost. You are more suited for high seismic areas. Each raise is based on the natural ground, suited for any types of tailings, drainage within the dam, and rate of rise is unlimited. Centerline construction is another form of slurry construction. Medium cost. They're acceptable in seismic areas. They're not recommended for permanent storage. Peripheral, so that's at the sides, discharge. Wide beaches. They have drainage within the dam, and they have height restrictions generally. Tailings filtered, there's usually they're almost like a landfill. They're just building up. So it's just like an earth embankment of tailings, but maintained in a safety manner. As we can see, this is a bit of an old picture, but the trends are still exhibited here. You can see that filtered tailings is going up rapidly. Co-disposal, which is a mixture between tailings and rock, has got very little go, but I'd say filtered tailings is the way we're going as an industry. But when we look at tailings, as we said before, as a consultant, I look at them at various stages of a mining project, ranging from the scoping conceptual stage down up to detailed design. Each have different levels of accuracy, from say 2% down up to 50% to 100%, and that's how much effort we have to put in. But with that level of effort, we have to still put a contingency, which is the level of uncertainty. The tailings dam design consists of undertaking site options, doing the layout, the staging, how it's going to be built, undertaking geotechnical site investigations, asking laboratories to do laboratory testings of the tailings and the soils based on new and previous samples collected. We have to characterize the tailings, how they behave. People have to do hydrogeological surveys and hydrological surveys like water balances, seepage and groundwater modelling, understand how the line is going to behave. People have to design the hydraulic structures, that includes the spillways, the decants, select slowing water pipelines and pumps routes, have to do static and dynamic stability analysis. We have to prepare the engineering drawings. We have to put the quantities for how much tailings we are going to deposit on the dams. We have to design the closure planning, and then we have to put in a report for Mr. Client. I say we have to design for closure because this is just as important as the operation. You may have a perfect project, but then if the project has not got a good closure plan, it may not get the go-ahead. So site selection. We need to understand the project, national legislation, the environment, the material properties that are going to be deposited. Depends on good environmental, it depends on good teamwork between geotech engineers, the environmental teams, geologies, and project teams. And it consists, when we look at project site selection, has to incorporate all aspects of the mining cycle: construction, commissioning and operation, and closure, and how it generally fits into the project site. This is our project in West Africa, and you can see here, there's all the current facilities in the far southwest corner. You can see my cursor, it's here, but we have to interlate it with all these other these aspects, like the crusher, the power plant, the dump leach. We have to relate it all together. So an option study consists of considerations as the topography, the geology, the environment, the mine infrastructure, the water courses, the catchment area, the land use, the capacity, how much tailings is going to be actually deposited, the construction economics, and then we rank all these accordingly and score them to find the optimum place. Then the environmental team come along, and they have the same. They rank each site based on the proximity to locations, villages, catchment areas, vegetarian, land use, ownership, mineral rights, visual impact, water courses again, impact on the water supply, local ecology and archaeology. And from that, we can find the optimum site. And then we rate them, and then we say, get the total and say, oh, look, these ones in red are the best sites to use, or these aren't good, the other sites aren't good because they haven't got these constraints placed on them. When we design a geotechnical site investigation for a tailings dam, we have to consider the foundation characteristics, the hydrogeological parameters, so that's like the groundwater level, how much water can come out of the hot ground and such like borrow material, which is the source build material, the stability, we have to check the stability of the ground, and we have to base it on international standards. So stages of conventional site investigation are very similar to any other kind of stages of a site investigation. We have to do a desk study, collecting data, doing maps, memoirs, previous reports. Do a site reconnaissance, so that's walking over the site, almost like a follow-up from the desk study, and then we examine the site conditions. Then we collect samples and sampling, and sanitary exploration, collecting, investigation of the geology, the groundwater, based on trial pits, boreholes, and geophysics, if we're lucky. Then we collect samples for examination for field testing and in situ testing. Then tests can be carried out either on site or prior to or during to the construction process. So this can be lab testing using disturbed but preferably undisturbed samples for geotechnical or geochemical properties. Then we write a report describing the ground conditions. So stages of ground investigation, this is the other stages. You come on site and it's a barren site. This is a site in Liberia before a tailings dam's got built. And then when we're on site, we have to deal with the locals, and this has its own problems in itself. Or delays in projects, and we still have to work in harsh terrain and hot weather if we're not used to it. So typical ground or geotechnical site investigation, field investigation tests we use. In boreholes, we use SVTs, permeability testing. When we're in the basin or the footprint of the tailings dam which is going to be developed, we can use CPT, Macintosh probe, CBR, vein testing, and dynamic cone penetrometer. These give us information about strength, and they help correlate with other properties. When we get samples from the boreholes collected, we can do a range of testing from classification, performance, consolidation, and strength testing. And these help us to derive settlement and rapid to short, long-term stability properties. Then at this sort of stage, the mine has some sort of idea of what the tailings is going to be like. So we can do a lot of testing. We can do classification testing. So this is very similar to doing soil mechanic testing. We can do classification. So this is moisture testing, particle density, Attenberg's, particle size distribution. Deposition, we can do shrinkage testing and specialist testing called air drying testing, settling tests. And then we can do permeability, odometer testing, triaxial testing, various forms, consolidated drained, consolidated undrained, shear box, lab vein. And then we can do rheological testing like viscosity, slump testing to see how the tailings is going to behave. We get all sorts of fancy, various charts like PSD charts, settling charts. We do typical analysis of the triaxials, consolidated and drained, to see how it's behaving. We can get specialist geochemists involved to see how it's behaving geochemically. Then we come up with a design criteria based on the flood return. So it's the probable maximum flood retention. So this is the operations with volume required in freeboard, which is the amount of free water available from the surface to the dam level. So we can use one and then we event sort of return periods to see the maximum flood and see how much the dam would potentially flood. This talks about, again, the event. So if it's a low event or to a high event, we have a return period of various stages, and we have to design for all these eventualities, a 1 in 200 to a 1 in 10,000 event, to make sure the tailings dam doesn't flood. And we have the same thing for seismic criteria, from low to extreme. When we do a seismic hazard, we can initially do a preliminary analysis based on internet searching of local area, or then we get a local expert to do a seismic assessment for us. When we do a seismic analysis, we usually base it on an operation basis earthquake or maximum credible earthquake. Then we can devise the mine waste facility class. This could range from low to extreme based on these return periods. And this is all dependent on the loss of life and these environmental consequences that we talked about earlier. Then other team members will develop a hydrological assessment. Then we can set up rain stations as soon as possible to understand the rainfall trends and extraction points. We can commence collecting meteorological data from local elevations. Water is critical to the project. We take advantage of exploration drilling to obtain information on water levels, material properties, and potential construction properties. So we do pumping tests. We take advantage of condemnation drilling. That's drilling that's been outside the remit area but has been abandoned to provide reliable information on water levels within the environments of the tailings dam. We can take advantage of plantation material properties to understand how the groundwater is, and we can use piezometers. We need an accurate topographic survey, so we use maps at various scales, 1 to 10,000 to 1 to 50,000. We use photographic mapping, satellite imagery, and local land surveys. We develop depth capacity, so this understands how much tonnage is going to be placed into the dam, understand the total tonnages being placed. We understand the pulp density from this. We understand the dry density, and then we need a good map. And I've just outlined the stages here. What does it look like? We have elevation versus tonnage. So this is how much tailings is going to be deposited with respect to the elevation, and how the project develops stage 1 to stage 4, and then closure. When we do a basic slope stability, as I said before, we can either do it we will have to do it on the maximum design earthquake, an operation basis earthquake. A basic slope stability analysis will be based on material properties, based usually on in situ testing properties, so it's CPT, or laboratory testing. So that's CU triaxials, or direct shears, or cyclic direct shears. Preferably, we're going to use CPTs because we find they're the more reliable. But if we don't have any laboratory testing, which we hopefully don't, we have a body of knowledge of other consultants in our company to help us advise for properties. We use our engineering judgments, and we base it also the quality of data. We assess for the peak and residual strengths, not just the cohesion and friction from one quick triaxial. We determine the critical slope and failure mechanisms. We define the slope model, the geometry of the slope to be analysed, the materials and types of occurrence, focusing on the prism, which is the wedge of the build material. Specific features such as the water table, the seismicity, and the tailings source. We run and verify the model and calibrate it with in situ observations or in situ properties and what we've got, and we compare against an acceptance criteria, which is the various loading conditions from construction before the dam got filled to closure or post closure. So each construction before reservoir filling, which is before the dam got filled, and during the long-term stability at a factor of safety 1.5, compared to closure at 1.2 to 1.3, and in the pseudostatic, which is a seismic case, we have to have a minimum factor of safety of 1. We have to assess the seepage and the dam breach. So we use a range of packages like CIIGGUPC, mud flow, and we do a dam breach analysis to see if the dam will breach, and flood. We have to manage water. Some things you can't control, like NOAA, but you have to manage water as best you can and cover all your eventualities. Water management involves developing a good water balance. So this talks about all the water, how it goes through the facility and comes in and out, the inputs and outputs, and you manage of water, how it flows through the system. So and when we talk about water, we talk about decant towers, we talk about how they're going to be used. Then we talk about the decommissioning and closure of the tailings facility. We want to prevent the long and short-term environmental contamination. We want to ensure the physical and chemical stability at closure and post-closure. We want to maintain resilience to climate change and its various effects. We want the area to be sustainable. So we want it to cover the 4 E's. We want it to be equity, environmental and economy and engineering. You want all those to be covered. So looking out, some words of wisdom, just I'm going to hopefully pass on. When you want to become a competent engineer, and I'm still growing after 25 years, you want to develop your skills, you want to take on challenges, you want to feel recognised, you want to feel respected and appreciated by others, you want to progress, you want achievements, and you want opportunities. And these all help you develop your competency with time. So top tips I would just like to pass on to one and all here. Have a curious mind and learn something new every day. Number 2, share your knowledge with others. This is so important for your advancements. Gives you confidence to share what you know. Number 3, skills. It takes about 10,000 hours to become master skill. So like some organisations and some societies and professional bodies, says it takes 7 years to be chartered. 10,000 hours is about that amount of time to become a professional engineer, a chartered engineer, to be a master of that skill. But I would say it takes a whole lifetime. Number 4, broken plots can be repaired from precious gold. When you've had a bad experience, you can learn from it and make something good out of it. If you had a bad site investigation or test result go wrong or bad analysis, you can learn from that and hopefully take something good from that and build it on for another project. Your attitude is very important as a young engineer. A journey of 1,000 miles begins with single steps. And finally, don't walk in someone else's shoes. You can't copy my path as a tailings engineer. So, or this lady's walking on the wire, but walking high heels across the wire. It's your path. You can copy principles and learn ideas from me, but you have to walk in your own path and try to be the best engineer you possibly can. And that's all I'd like to say. Thank you very much.
Okay, thank you, engineer.
Thanks, engineer.
I'm gonna give this
Thank
word.
you very much, engineer, for your excellent presentation. We consider that it has been a very interesting topic, and I am sure that the audience will enjoy and learn a lot thanks to you. Ingeniera Shirley, ¿quiere argumentar algo? Perdón por interrumpirle.
No, it's okay. Okay, engineer, thank you so much for this amazing presentation. We consider this has been a very interesting topic, and we're pretty sure that the audience has enjoyed and learned from you and all your family that you have showed us, and because of your knowledge and your wisdom. So now I'm gonna go with the Professor Roman, who is about to make you the questions from the public, if you don't mind. So Professor.
Thank you, Martin, for such a great presentation. We have some questions from the audience. First is, why the credible mode is not associated with probability?
I'm thinking on the spot, okay? I think that because every project is specific, if you said a probability, you're based it on case histories. Does that make any sense? I think it's because you got to look at every project as a specific thing, and a probability would base it on a lot of projects.
Oh,
yeah,
I got it. Another question is, do you have some comments on answer-based techniques for monitoring tailings dams?
What do you mean? Can you repeat the question?
Like the interferometric synthetic radar, like it's widely used, but some are that they might not be so reliable, or are that used in most tailings dams for the observational method.
Yeah. Still, monitoring is the best thing. If you can monitor as you build and as you deposit the tailings. So you have to have a whole range of instruments like piezometers, extometers, You can use satellite monitoring. Just use a whole range of monitoring equipment. Don't just use one type, because you're monitoring the water levels, you're monitoring flow rates, you're monitoring how pore water pressures, you're monitoring everything. Does that answer your question? It probably does.
Yeah, of course.
Yeah.
Well, another question, and this is a very interesting one, is based on your experience, what will be the main challenges for implementing filtered dry stacking in large mining operations? Let's say production over 20,000 tons of tailings per day.
The biggest problem at the moment is the cost. Most mining operators would want them the cheapest disposable method, and that's why I focused on slurries mainly, because that's the cheapest way. That's the way in Europe they still traditionally have deposited. But dry filtered tailings are expensive, less environmental cost, but maintaining that level of, we say, dryness and that level of dry density that you require to get an efficient stack is hard to maintain. So you need good quality control on your stack.
Great. One final question is, why do you think that the observational method proposed originally by Professor Peck is still poorly understood?
That's people, perhaps people haven't read it properly, or they don't think something's going to go wrong on their project. So they don't think they need to observe things as much or monitor things. And what I've learned from 25 years in working in tailings, or 20 years in or any project, you have to keep on monitoring. Because monitoring, as I say, is so important, because that's why I keep focusing on like Bruandinho and such Mount Pollitt, not because I've seen that personally, but I don't want that to happen to me. If I've designed something, I don't want something to happen. Because I think, I'm working on a project, another project now, and we're talking monitoring. Say how important we have to keep on monitoring and monitor things in real time. We can't have the monitoring data 6 months behind and looking at it 6 months later. We need it today to see what's happening today. I think people, and there's almost like people want to build as quickly as possible without thinking it's safe, and then thinking it's safe and then doing it, carrying it on. Does that? Yeah, that's how I think.
Oh, thank you very much.
So
then we'll have some final questions from the students. Oh, sorry. I think we have some final questions from the students, so we can finish this great lecture. Could you please ask them?
Engineer Griffin, can you hear us?
Yes, I can.
Okay, thank you. Professor Roman has asked if you have any words for the students.
Any
speech words to like a goodbye. In advance, we want to thank you very much for this excellent presentation. All the members of this chapter are very grateful for agreeing to share your valuable experience and teaching out with us. On the other hand, we want to leave you with the invitation to participate in the future conferences with us. And we thank you again for your brilliant participation supporting in this Congress, wishing you all the success and many blessings. So if you would like to share some goodbye words, we are all ears to hear you.
It's again saying thank you very much for this unique opportunity to share something of what I know to younger people. And I say I'm still learning, that's why I didn't touch on everything. I'm giving it as general as possible, not to sort of talk about one project, trying to talk about give you a big flavour and say it's an exciting area to go in. If you like risk, you like ground investigation, geology, engineering, geology, love geotechnics, it's a great area to be in. That you won't get bored.
We're pretty sure of that, engineer. Thank you so much for sharing these words. My partner Sandro might say something to you, maybe. Please, Sandro, if you would like to say something to the engineer. I'm pretty sure he's very pleasure to have been here.
Yes.
Oh.
Sí, te escucho, pero te escucho un poco entrecortado. Creo que es mi señal.
Si quisieras decirle algo al ingeniero.
No, sí es mi señal. Dame un toque, ingeniero Yulis.
Okay, well, Engineer Griffin, he's coming about 1 minute, maybe.
Okay.
To say goodbye. We are pretty pressured for this, and it was an honor to hear you, to learn from you and all your experience. It was really great for that.
Yeah. I realised in the practice when we talked last 2 weeks ago, I showed you the wrong slides.
Mm-hmm.
I had them all prepared, and I picked up the wrong file from my folder. So,
but we could fix it in the end.
Yes, it's good. But as I say, that was only an introduction. It's not all the answers, because you have to look at every project on your own case-by-case basis. You can't.
Exactly. Maybe sometimes this could happen.
Yeah, or we read a book and we think the book has all the answers, but books don't have all the answers. We have to still go on the site and look at how the soils and how the tailings are behaving. And
well, we have some final question.
Okay.
There are many students in the audience, and what would you recommend to the students who are in this tailings engineering? That's a kind of new subject. What would you recommend them?
What books, or what to do?
Yes. What would you recommend them to study, or
I recommend
what?
Civil engineering, geotech engineering, have a good understanding of geology, have a good understanding of hydrogeology and risk management. So it's just being a good rounded engineer. Because as you see from the talk, there's a lot of things interrelated. So you've got to see this big picture of how not just see yourself as a geotech engineer who does a road building. You can concentrate on that. That's a very small aspect of geotech, but a tailings dam engineer will see a lot of interrelating things, all interrelated together. So you can't get always bored, and you're not just seeing the project as it's being built. You're seeing it from the development to its closure, and it has all these different stages as well with respect to time. So I wouldn't get put off and almost get put off by the risks and say, oh, it's going to fail. There's lots of bad publicity, because there's a lot of, and we all get put off by people saying we're not going to use mines in the future because of the environment, but people still will want their mobile phones with the metals inside them. We will still need a car. So we will still need mining. So we need engineers to help design the mine waste facilities. So some areas of geotechnics might seem more attractive in the future, but we're still going to need mining and tailings engineers. So don't get put off if it seems not a very attractive career.
It's very attractive. I say to the students, it's a very interesting field of geotechnical engineering. Well, thank you very much. I don't know if you have some final words.
Thank you for having me.
Thank you so much, Engineer. My partner has some connection problems, but he would have loved to say thank you again.
Okay.
It was such a huge honor to us. So if you would like, we have enjoyed this and we are really pleasure to have you here once again. Thank you once again.
Thank you. Have a great night or have a great day.
Hope to see you next time.
Thank you very much.
Okay, yeah. I'm happy to do it next time or something. Okay.
Thank you
Okay.
so much. Engineer.
Adios.
Have a great. Adios.
Bye.